Open the pod bay doors, Hal.
I'm sorry, Dave. I'm afraid I can't do that.
What would you do with a brain if you had one?
Do? Why, if I had a brain, I could...
Miles per hour.
I could while away
46, 56 degrees.
Hi, I'm Melanie, and I am a mechanical engineer from Lawrence Livermore National Lab.
Hi, I'm Julie, and I'm a mechanical engineer.
Hi!
Hello!
Hello, I'm Eric Duoss. I am a materials engineer at Lawrence Livermore.
Hi, I'm William Smith. I'm a mechanical engineer at Lawrence Livermore.
And I am Chris Spadaccini. I'm an aerospace engineer also at Lawrence Livermore National Lab.
Okay, so without further ado, get started. Well, I'm guessing that most of you are here because you've heard about 3D printing and you've heard about how it is going to change our world. And so we are here to take you on a journey through the wonderful world of 3D printing and show you how at LL&L we create materials that have unique properties that have never before been observed. Before we get into all that, we're going to give you a little background information on materials and how 3D printing fits into our world. So materials are around us all the time, but we maybe don't think about them. So if you look at this house, for example, there's many different types of materials that make up this house. So there are the brick, the shingles, the windows, the insulation of the walls, the carpet inside, the tiles. And each one of these materials has its own unique properties and is made in a specific way for its application. Materials can either be used in their raw form or as an input into a manufacturing process. For instance, the solar panels on these houses are made with a carefully constructed material that allows them to absorb the sun's energy to produce electricity. So the way they're made is directly tied to their application. Another way in which material science and manufacturing technology affects our day-to-day lives is through our communication devices. In a time where being connected is so important, we rely on our smartphones and laptops to keep us connected to the world and in the loop on what's going on. So I want you to take a moment to look at these devices and ask yourself a couple questions. How do the touchscreens on these devices respond to our touch only when and where we want them to? How do the screens display color or show detail from the messages that we get? All of these questions are part of a bigger theme that we will cover in this talk, which is how are things made and how can 3D printing be used to make them better? So before the Industrial Revolution, pre-1800s, everything was made by hand and this was extremely time-consuming, difficult, and often dangerous. We had a small number of skilled craftsmen who put in a lot of effort for very little output. And so this affected the day-to-day lives of the people at this time. It made their lives very hard and they had to put a lot of energy into completing the tasks necessary in their lives. So if you think of the phrase, work smarter, not harder, that was not happening in this case. So on the onset of the first Industrial Revolution, in the beginning of the 1800s, our ability to make things increased dramatically. And this was partly due to the adoption of the factory system and division of labor, as well as the use of machinery in these factories to accomplish tasks. So all of a sudden, we're able to make things in a much more efficient manner, and therefore this time was a time of huge innovation that had never before been seen. Now with the second Industrial Revolution, at the late 1800s, we see these ideas be expanded beyond this assembly process and the additional use of machinery in the manufacturing process. This time is also known as the technological revolution because science and engineering played such a large role in advancing manufacturing technology. For instance, the introduction of electricity into factories has been called one of the most important engineering achievements of the 20th century by the National Academy of Engineering. Additionally, because of the widespread use of railroads, telegraphs, and later telephones, people, and more importantly their ideas, are able to move more freely throughout society. At this time, we also started to see an increased interest in the development of techniques to make steel and iron, as well as the development of new materials such as alloys. Material science and chemistry became more and more developed fields at this time. So because of the innovation at this time, we now have automobiles, we have electricity in our homes, steel to make our skyscrapers, and very importantly, phones in our homes and in our pockets. So some say that we are now at the cusp of the third industrial revolution, and 3D printing is at the heart of that. So in this new manufacturing process, basically what happens is that you would create a design using your computer, you would then build that design using a 3D printer, and voila, out pops custom fabricated parts with all of the complexity that you need. What this also means is that anybody who has access to a computer can therefore be engaged in the advancement of technology. So the distance between your imagination and the realization of your ideas is getting smaller and smaller, and that is extremely exciting. So hopefully at this time you understand why people are so amped up about 3D printing. We're seeing 3D printers everywhere now, and they're being used to make things from clothing to cars to computer parts. So you may be wondering at this point, how does 3D printing actually work? So at this time, I'm going to have Julie come out and explain to you exactly what's going on.
Okay, thank you, Melody, for the introduction. So, before we dive too deep into how 3D printing works, let's first actually define what 3D means. 3D means three-dimensional, and that can be described with the Cartesian coordinate system. On screen we have one, and many of you are probably familiar with this in your math and physics courses, but for those of you that aren't, what it does is it gives every 3D object an X, Y, and Z dimension. So, take me for example. My width is my X, my depth is my Y, and my height is my Z. Now, why is 3D printing, otherwise known as additive manufacturing, sometimes better than traditional or subtractive manufacturing? Well, on screen we have a video of a lathe. And what a lathe does to fabricate parts is it carves away material. This can be extremely hard to make really complex parts and features, especially in the inner volume of that depth. 3D printers, on the other hand, only place material where you need it. So in this way, it can actually be very easy to create complex features. Take this bowl, for example. It takes us just as long to make this bowl with holes in it as it would a solid bowl. So because of the way that these two manufacturing processes work, 3D printing actually minimizes waste compared to subtractive manufacturing. So with subtractive manufacturing, you start with a bulk piece of material. It can be metal, plastic, wood. You then have to carve away that material like the video we saw on screen, the first video. And once you have your 3D structure, you're left with a lot of waste, all those chips we saw flying off the screen. Additive manufacturing, or 3D printing, starts with raw materials, say powder, filament that I'll talk about later. And because it only places material where you want, once you have your 3D structure, you're actually left with little to no waste. So we actually have a 3D printer here on stage, and I'm going to talk a little bit about it. So this is a Makerbot. And basically how you run one is you would create a 3D model from a computer-aided design software. Once you have your 3D model, we chose a unicorn, you import it into the 3D printing software, and what that software does is it slices your 3D model into 2D layers, so think like a deck of cards. The printer then has, let's see, a plastic, it looks like a plastic wire that feeds through a hot nozzle. Once it reaches the nozzle is at 220 degrees C. Once it reaches the nozzle, it's going to melt. And because it's melting, the nozzle can draw that plastic around. So it draws one layer, the base plate here lowers, and then it draws the next layer until you have your full structure. So actually when you look at 3D parts, you can see that they're made up of lots of little tiny layers. I don't know if you guys can see these. So basics on how they work. Okay, so, Melody alluded to this earlier, but one of the really amazing things about 3D printing is that it allows you to rapidly turn your ideas into real physical objects. So every day the people in our lab come up with these crazy ideas, and we then go and draw up those ideas in something called computer-aided design, or CAD software. Once we have our CAD file, we export that into the 3D printer, push a button, and out comes your part. So it's not exactly that easy, but those are the basics. And often when fabricating any type of component, you realize that you want to make some changes. So you have to go back to your design, tweak a few things, and then refabricate it. This is what's known as the design iteration process. And this can take a long time when you're dealing with subtractive manufacturing because it's complicated to get those parts printed, especially in a short amount of time. So 3D printing actually dramatically shortens the time of the design iteration process. 3D printing also opens up a world of new design, so this is really cool. We can now make things that we couldn't make before 3D printing was a reality. So on screen, I have an example of a few things. I know you guys are probably thinking, number one is not new. That's the Eiffel Tower. It was built in the late 1800s. But the amazing thing here is that all of these structures were built in one piece, so one print. The Eiffel Tower was built in 18,000 pieces. And that's what's really amazing here is that because 3D printing only adds material where you need it, you can get these really complex features, and especially on the inner volume of structures. It would be really hard to have to carve out that volume with just a block of material. Another really cool thing, if you look at number 4, that's something called a planetary gear. And directly off the build plate, this gear actually spins and moves. So you can build fully functional pieces all in one print. So no assembly required. So now I'm going to hand it off to Eric. He's going to talk to you about what we actually do with 3D printing at LML and why we like to come to work every day.
Okay, thank you, Julie. So, let's see, what do we do at Lawrence Livermore National Lab with 3D printing? We've told you a lot about the history of manufacturing and materials. We've introduced the benefits of 3D printing, but what specifically are we doing? Well, we're trying to innovate. That is, we're trying to create and dream of new technologies and advance those 3D printing technologies. So, we also look at 3D printing or additive manufacturing very holistically. That is, it's much more than just the process itself. So we look at things like feedstock materials. What do you input into the process? And how can you engineer or design those materials that are fed into the process? The processes themselves. So we try to advance existing processes, but we also try to invent new processes. Modeling and simulation. So at Lawrence Livermore, at any given time, we often have several of the largest computers in the world, the fastest, most powerful computers in the world. We call them supercomputers, or high-performance computing. So we look at how can we use those computational resources to better understand the processes and the physics that underpin those processes. Designs. So that's one of the really incredible things about 3D printing is how three-dimensional design space has really opened up. And in fact, we spend a lot of our time trying to convince designers and engineers and architects and so forth to really take advantage of all of the complexity that these processes afford them. And lastly, applications. So we're talking about materials and manufacturing. As you can imagine, those are very enabling technologies. Who doesn't work with materials? Who doesn't benefit from manufacturing? In fact, we really like exploring the design space and exploring the application space and dreaming of new ways to use these. Whether it be in electrical systems, printed electronics, for example, stretchable, flexible things, magnetic devices, optical devices, structural mechanical things. things that have really interesting thermal properties, chemical resistance and so forth. So there's lots of end applications, end uses that can be enabled by 3D printing. In fact, that's what keeps it exciting for us, is we're always learning. We're always learning about new fields with 3D printing. So I mentioned feedstocks. What is a feedstock? A feedstock is literally the stock of material, or the stuff, which is fed into the printer. Okay? So there's a saying in computer science, garbage in, garbage out. I think you know this from just your daily life. You pay attention to what you eat. And why do you do that? Because it adds nutrients, it gives you nutrients, it gives you energy, and it allows you to function. So what goes into the printing system is very important. What we show here is just the commercially available feedstock. It's a thermoplastic filament that's used for this type of printer, fused deposition modeling printer that Julie described. Okay? Now these are commercially available materials. We don't do research on these types of materials at Lawrence Livermore, but I think it's important to note that we do design custom feedstock materials for various 3D printing and manufacturing processes. Also, those feedstock materials can take many forms. In this case, they're a filament or a wire. They can also be a powder. They can be a resin. They can be an ink. Many different forms, okay? So, one example of things that we actually synthesize and formulate at Lawrence Livermore are nanoparticles, okay? And nanoparticles are really interesting and new materials that have interesting behavior. And I'll just pose a question to the audience. What does the nano and nanomaterial mean? Anybody know? Raise a hand, raise a hand, raise a hand. Anybody know what it is? Who's got it? You got it? Yes. Small. How small? What is the nano? Nano small. Yeah, so the nano is the prefix for the length. You know? Micro is actually a different prefix, so that's a different length scale. But you're right. Come see me, I've got something for you. A 3D printed unicorn is coming your way after this. So nano refers to nanometer. Meter is the unit of length, nano is the prefix. Nano is incredibly small. So think about taking your hair. I heard microscale. There's a micrometer. Turns out your hair is on the order of 100 micrometers. Think about taking your hair now and splitting it lengthwise, splitting it in half. Now take each of those and split them again. And split until you have 10,000 pieces of your hair. Okay? One of those strands has a diameter on the order of a nanometer. Really small, in fact, so small you can't even see it with your eye. In fact, you can't even see it with an optical microscope. You need a sophisticated microscope, like an electron microscope, to actually make out those discrete particles. In fact, that's what we show here on the bottom. Those are scanning electron micrographs of different tailored nanomaterials that we're able to make at Lawrence Livermore. So you can see with chemistry now we can change the shape, the size, and the morphology from things like pyramidal types of architectures of particles to cubic types of particles to wires. Okay? In fact, I brought some nanoparticle suspensions that are on the light box here. And I don't know if we can zoom in on this. Okay. But you can see they're all different colors, right? That span the rainbow. Roy G. Biv. Perfect. Okay. Here, I don't know. All right. Another question for the audience. What is giving these suspensions their color? Anybody want to take a guess? Yes, you.
The nanoparticles.
That's right. What about the nanoparticles, though? Why are they all different colors? Please. Yes. Different material they're made of. It also turns out two other things are very important. Come see me after this. I got something for you. Yes. Sorry? Light definitely matters. The color that you see is actually being reflected from them. It means they're absorbing other wavelengths. But there's two other features of the particles themselves that are important. give rise to the color. Anything? Yes, please. You got it! There's shade. One other thing. See me afterwards. What about you? Yes. And their size. Very good. See me afterwards. I got something for you. Yes. So the color that you see is actually from not only the chemistry, that is what they're made out of, but their shape and their size. In fact, some of these are the same exact material, the same chemistry, gold, for example, but they can be made at different colors. In fact, they're different colors than what you see for gold at the macro scale. Okay? Really cool stuff. But that was an aside. We take these now and we can actually make feedstocks out of them. We can make inks or resins. And, importantly, we can make inks or resins that have all kinds of interesting new properties. I mentioned some of them. They can be electrically conductive. They can be thermally conductive or insulating. They can be magnetic, have interesting optical properties, and so forth. Okay? So we return to the slideshow. Now, these feedstocks can be made of different material classes. And by material classes, I mean metals, ceramics, glasses, polymers, or plastics. And depending upon the material class, you can have different material properties. We all know metals. Metals are extraordinary engineering materials. They can be really mechanically strong. They're also electrically conductive typically, also thermally conductive typically. Okay? They're somewhat hard to form with manufacturing processes. They have somewhat good thermal resistance, whereas ceramics or glasses have very exceptional thermal resistance. You can keep them to very high temperatures. Glasses have unique optical properties, things that lenses and different optics are made out of. Ceramics and glasses are harder to manufacture. Okay? And then plastics. Plastics are inexpensive, they're easy to produce. They have a range of material properties that you can achieve. But they don't have, so the thermal resistance, you can't take them to as high temperatures as you can with the ceramics. So I'm going to welcome Will out here, and Will's going to do a demonstration to illustrate how different materials respond to an impact.
Thank you, Eric. Now, like Eric just mentioned, we have three material classes that I'm going to demonstrate. So here, representing the metal, I have this metal Coke can. Representing glass and ceramics, we have this glass light bulb. And representing polymers and plastics, I have this plastic Sprite bottle. And safety first. Because this test that I'm going to be performing right now is an impact test to show how the different materials respond to impact. So first we have the metal can. So you see, it undergoes permanent deformation. It stays intact, but there's no way it's going to be able to recover from this. Now, the light bulb, on the other hand, this thing essentially shatters or goes through a fracture, and it's also permanent deformation, but it does not stay intact, so there's no way it's going to ever be able to recover. Now, the plastic bottle, on the other hand, even though it's weaker, you hit this with the hammer, it deforms, and it stays intact, and it's also able to recover. This just goes to show that plastic is a lot more elastic than the metal and the ceramic, and it just goes to showcase that when you're choosing your material that you want to manufacture, you need to keep these different properties in mind.
Okay, thank you, Will. And we can go back to the slideshow. All right, so that's great. We told you about material properties. Now, how do we actually take these different materials and print them? Okay, so we developed some new processes, often with academic collaborators at Lawrence Livermore. I'll tell you about a few of them today. Projection microstereo lithography. It's a mouthful. Who wants to say that 3 times fast? No, I'm just kidding. So I have an animation that shows what this is, but it's a photochemical technique where you take a computer-aided design model. It's in the computer now, 3-dimensional. You slice it into layers. You take one of those layers and you project it with a spatial light modulator, similar to how we're projecting our presentation here today. So you have some defined image, white and black for light, put it through some optics, and you expose it to a liquid resin. Wherever that liquid is exposed, This is a carefully designed resin. It's photocurable. So it will actually transition from a liquid to a solid. And as we change that pattern, that light pattern on the fly, just like you can do with your projection system, you can change the way you're patterning the three-dimensional part as you're lowering that part into the resin bath. Okay, so you can get really complex three-dimensional geometries with this particular approach. Now we have a process called direct ink writing, where we extrude material very similar to this printer here shown here today. But instead we replace the heated printhead with a printhead that works at room temperature. The key is we design inks that can flow at room temperature. They have very particular flow properties, or what we call rheological properties, such that they'll shear thin in the presence of the nozzle. They're being sheared, they lower their viscosity or their resistance to flow. But once they exit the nozzle, they rapidly recover their gel-like state, so that you can print a three-dimensional part layer by layer. Also, what's really cool is you can print conformally onto non-planar objects, such as this animation shown. Okay, so you can put deterministically deposit onto very complicated shapes. That was an example of sort of an antenna-like architecture we were making. Okay, so now those previous processes would either hit light or use light in a two-dimensional pattern to get a three-dimensional part, or raster a point source. That was the nozzle. We've got an entirely new process which we're showing you here today, in which we create a hologram, or a three-dimensionally defined pattern of light, and put it into the resin, and in a single shot now, we can essentially print a 3D part. So this was completely invented at Lawrence Livermore, and frankly, you're some of the first people to ever see this technology. So you can imagine this could rapidly increase the throughput of 3D printing technologies. Yes?
How long did it take first to do that? How long did it take to do that size?
So the question is, how long did it take to print a part of that size? So the answer is a matter of seconds. And then, the real answer is it's been a research and development project for years to understand the process, to get to that point. Okay, so you can also work with metals. So there's a process called selective laser melting, where you have a metal powder bed, and you roll out a layer of powder, and you can raster a laser across the surface. And the laser has sufficient energy to locally melt wherever it hits the powder, and fuse those particles together. Now, if you have a defined laser pattern, wherever you don't hit the powder, of course, it stays free-flowing. And as you roll out other layers of powder, you can build up a complicated metal part. Aerospace industry is extremely interested in this technology. And it's very important to really understand, as I mentioned, the physics of these processes through things like modeling and simulation. So what I show here is actually a metal powder bed, represented by those spherical particles in blue. And in the computer now, we're rastering that laser across the surface using supercomputers. And we're looking at how does the morphology and the microstructure, the thermal energy that's input into the system change. So I'll play this. And you can see that the red spot is essentially the leading edge of the laser. We're looking at the temperature distribution through that part, through that powder. And we're seeing how does it sinter or how does it melt. This is very important because the microstructural effects that occur at this length scale and below affect the macro scale properties of the metal. Okay, so there's a lot that goes on with modeling and simulation. I'll also say that in terms of design, it's very important to take advantage of the design space. And we use supercomputers, you can use cloud computing, you can use personal computers to design components for 3D printing. In fact, that's what Will is going to tell you about next.
Alright, so you guys just learned about a lot of the processes that we use at Lawrence Livermore. Now I'm going to talk to you guys about the strategy that goes behind the designs that we do. Eric just alluded to the fact that we often use computers to aid us in our design process. In this next video I'm going to show you, provided by our partners over at Aeronautics, gives a really succinct overview of how the process is carried out and the different possibilities that lie within it.
What if you could come up with thousands of options for a single design without drawing, all of which meet specific goals set by the designer? And from those options, pick the one design that delivers on the most important criteria, the design you couldn't possibly have imagined. This is Generative Design, a technology that harnesses massive computing power, creating forms with precise amounts of material only when needed, achieving maximum performance while wasting nothing.
Now, you may have noticed in that video there were a lot of really funky designs for that drone, which you wouldn't be able to intuitively come up with if you didn't use computers to aid you in that design. And that's because, as he was saying, you can use the software to only place material where you really need it, given on its expected environment. And taking this approach, this is how we design our architected materials. And when I say architected, what I mean is the idea is that instead of having just a bulk solid chunk of material, you instead infill that same volume with a lattice of beams that are connected together in a very intricate way to have lower density but still maintain relatively higher strength. And one good way to visualize this is to draw a comparison between the Eiffel Tower and the pyramids in Egypt. Now, the Eiffel Tower is twice as tall as the pyramids, yet it's almost 1,000 times lighter. And the reason for this is pretty obvious. You can see that instead of just a giant pyramid of metal, it's made up of tiny little beams, well, relatively small compared to the full size, that form a void space, and this would also make it a lot easier for you to build this structure because it's a lot less weight for you to carry. Now, keeping this in mind, when we are designing our own materials in the lab, we need to know where our materials fall on the spectrum of existing materials. And we do this by looking at a material selection chart. Now, this chart looks really complicated, but it's actually really simple. So on the bottom horizontal axis, you have your density, which just translates to your weight. So it tells you how heavy or lightweight your material is. On your left vertical axis, you have Young's modulus, or stiffness. So how squishy or stretchy your material is, essentially how easily your material is going to deform to a force that's applied to it. So you see in the top right, you have your really heavy and dense metals. And as you get lower to the left, you get your weaker, lighter polymers. And then as you get further down to the bottom left corner, you have your foams. Now, the interesting thing about foams is that they have void space similar to the architectures, but they do not have the relatively high stiffness. So this is the area that we want to get into. So you have this, you maintain that same low weight, but have higher stiffness. And you can imagine that a good application for this would be in aerospace applications, because a lot of your fuel cost goes into how much weight your aircraft is carrying. And we achieve this by making one of these little unit cells that you see here. This design is called the octet truss. And if you look closely at this, you'll see that there's a lot of beams counteracting each other. They meet at nodes so that when you apply a force to it, there's always a beam acting in the opposite direction. And this next video I'm going to show you is again by a partner set. It was done by me using a software provided by Autodesk. It's called NetFab. And I'm going to show you the design process of making one of those octet truss unit cells. So you have your empty unit cell, and you have to fill it with the connecting points, or the nodes, that connect the different beams. And the nodes are the little spheres that I'm placing in all of the different corners and edges and faces of the little void cube. So once I have all of the nodes placed, I then have to go in and connect them with the beams. And the beams are going to be the solid material that you end up actually printing. So I'm placing all of the beams around the cube. But right now, these beams don't have an actual volume or physical size. They're just visual representations. So I'm going in now and assigning an actual shape and size to each of the beams. So now that I have my shape set, and I have to go in and assign them to all of the beams, and then now I have my full-fledged 3D model. Now that I have my 3D model, I'm going to tile this and repeat it in the 3 different directions that Julie mentioned earlier. So I tile it in the X, I repeat it over in the Y, and then I stack it up higher and higher in the Z. And you notice that as you repeat this unit cell over and over and over again, you can look back at it, it resembles the simple solid bulk material, but you know that when you zoom in closer to it, you'll see that intricate architecture design, which is something that you can only make via 3D printing. Now, architecture isn't only something that comes out of the lab. Architecture is something that happens in nature and it inspires us to make the materials that we make. And one type of architected material or lattice material that everyone's familiar with is a honeycomb structure. It's a lot of little hexagons that are tiled in 6 different directions. And where you can see this popping up in things that we make as humans is in chain link fences, or in pavement when you tile down little bricks, or for structural purposes, between 2 layers of sheet metal, where you can get a much lower density because you see there's a lot of void space or air in there, but you don't have to compromise on your strength because it's still really stiff in the low direction. Now, another really cool instance where you see architecture at play in materials is in the exoskeleton of shellfish. So this clam that you see at the top, you know that clam shells are really hard and really strong and difficult to break into. And when you look closely at it, you'll notice that it's not a homogeneous smooth surface. It actually has a brick and mortar structure of tiles that are stacked next to each other. Now, this shrimp on the bottom, on the other hand, it has a claw that it uses as a hammer. And this hammer, when you zoom into it really close with a microscope, you'll notice that it has a structure similar to the spiral staircase. So between each of the layers that you stack up in the Z direction, or in the height, the layers actually rotate between one another. And I can let you guys take a guess as to who you think would win if you pit these 2 different types of architected armor against one another. So you see the magic shrimp going in for it. And just like the light bulb I broke earlier, the clamshell starts to break, and it's a sad day for the clam. Now, I'm mentioning all of this to drive home the idea that when you add architecture and complexity into your material, and in this case through evolution, you can enhance the material properties of your final product. And keeping this idea in mind, Chris is going to talk to you guys about the actual things that we make in the lab using architected materials.
Great, thank you. So now that you've heard about 3D printers, how they work, all the feedstock materials we can put into them, how we do design, and this concept of architecture and architected materials, I'd like to pull it all together for you a little bit, show you some of the interesting materials and structures we've been able to fabricate at Lawrence Livermore and how they actually perform. So for example, we have this octet truss, which Will introduced to you just now. We've been able to fabricate this at many different length scales using our additive manufacturing or 3D printing processes. In fact, the one you're looking at now was printed using our Microstereo lithography that Eric introduced to you. And it's very stiff and strong structure, but it's made up primarily of empty space, as we'll explain. And you can take that unit cell, and if you remember, we talked about the X, Y, and Z dimensions, and you saw Will do his design. We could tessellate that unit cell in space, which means to repeat it in X, Y, and Z, and create this larger scale lattice with many thousands of unit cells, all 3D printed. And as you step back and look at that piece of material, or that structure, it starts to really look like a material that has the properties that you designed through the structural layout. So again, very lightweight, but strong and stiff. And as another example, you can see here one of the materials that we were able to print, and how it can hold up many times more than its own weight. You see the material at the bottom, again, one of these unique structures. The blue arrow is pointing at it. It weighs only 6 grams. But it's holding up 180 grams of weight. So that's 30 times its own weight. And in fact, you could do more than that. That's just how much we could actually balance on top of it for the photo. But again, you can see these really unique properties that we can achieve through the concept of understanding the materials, laying out the structure through the sophisticated design, and the 3D printing processes. We can get even more sophisticated if you take a look at this piece. This piece, again, was printed with our Microstereo lithography, but then it was coated in metal, so it's actually made of nickel. We removed the plastic from inside of it through a chemical process. And we're able to build this fairly large piece of material, many centimeters in size. But it's what we would call a hierarchical, or in this case, even fractal material. If you zoom in on it, you can see little structures within the structures. So at various length scales, we're adding more and more interesting features and structure. And because we can do this, we can get even higher performance out of these sorts of materials. So this one really approaches the theoretical maximum for strength and stiffness at low weight. So we not only work on materials that are very strong and stiff and light, we also work on soft materials. The structure you're looking at here was printed with the direct ink write process that Eric explained, and it's a polymer or a plastic. It's very soft and squishy. It's the kind of thing you might find in your sneakers or in your football or baseball helmet. We call it a mechanical energy absorbing material. That means as you shock it or you hit it, it actually absorbs the impact of that strike. And what you're seeing here is somebody's finger pushing down on the material. And again, you'll notice that it's actually structured. It's these filaments arranged in a wood pile type architecture. You could change that architecture and change the properties of the material, change the amount of mechanical energy it absorbs. As an example shown here, we have 3 different pieces. On the left, we have just metal. The next piece in the middle is one of our printed structures that absorbs mechanical energy, a soft structure. And then on the right, we have a different printed structure where we laid the material out in a different way to better absorb the mechanical energy. And you can see from the golf balls bouncing that the last material absorbs the most mechanical energy. So we can design it, create the structure, and have the properties that we want to better absorb energy. So you would want the structure on the far right, the architecture 2, to be the one in your football helmet. So now I'm going to invite Melody and Will back up to do one more demonstration for you. We're going to talk about yet another interesting material property that occurs in nature that we can manipulate through architecture, design, and 3D printing. This property is called Poisson's ratio. You may not have heard of it, but it's actually a very fundamentally simple property. So what Will and Melody have here is essentially a giant rubber band. As they pull on it, what happens? The rubber band gets skinny in the perpendicular direction. So we experience this with almost all materials. If you pull on them, they stretch. However, and we would call that a positive Poisson's ratio. However, if we can go back to the slides, through the concept of advanced design and material architecture and printing, we can actually manipulate this property to be negative. For example, as we pull on this printed material, it actually gets fatter in the opposite direction. Completely the opposite of what natural materials do, all through design, printing, and manipulation of the material's structure. So we do a lot with these mechanical properties and these architectures, but there are other properties we can manipulate through this general concept. For example, pyrotechnics, things that go bang and have a flame. So these animations you're seeing here describe a scenario where we could print a material. We call it a thermite material. It's essentially a pyrotechnic, kind of like a firecracker for fireworks. And we arrange them in a parallel arrangement where you might call it a channel. You ignite it, and the flame propagates down this channel very quickly. Now, if we tried to do the exact opposite and arrange them in the perpendicular direction, we might call these hurdles, for example. We can print the exact same material, and you can see the energy propagates forward in a very different way. So we're starting to manipulate a different property other than mechanical and structural properties. We can do this again through advanced 3D printing processes and design of materials. So we actually made these 2 structures, and we tested them, and you'll see that here in this video. So on the bottom are the channels, and on the top are the hurdles. And you can see how much faster the flame propagates down the channels versus the hurdles. And it's very much because of the phenomena you saw in the animations prior to this. And one other thing to note is that in the laboratory, there's a bang and a flash of light, and this entire event is over. It takes about 10 to 20 milliseconds, just a fraction of a second. So we actually recorded this on high-speed cameras, slow it down, and observe how the energy moves forward or how the flame propagates. Another really interesting material that we've been working with now is something called a shape memory polymer. We can print materials as flat pieces or in certain shapes, and if you heat them up or add electricity to them, they'll actually fold up like origami later in time to create a different structure. So that's what you're seeing here. These materials were printed in many cases in a certain configuration, then heated up to a certain temperature, at which point they fold up to form a completely new structure. Many people call this 4D printing now. It's a new name for this because the 4th dimension is time. The structure is actually changing later on in time when you actuate it with a thermal or electrical energy. Finally, something that I think is the next frontier in 3D printing and architected materials is what we're calling multifunctional materials. So this is our same soft material that we showed you before with the golf balls, but now we added something to it. Now, if you recall, Eric talked about those nanoparticles, those very tiny particles that we can make in the laboratory. We can take metallic nanoparticles, put them in some of the layers, right into the material that's printed, and now you actually have an electrical pathway in the material. So not only is the material absorbing mechanical energy, it's also responding electrically, as you can see from the multimeter on the left. So the material is providing the mechanical performance you want, but also is self-sensing and providing an electrical response. And this is what we would call a multifunctional material. So before I turn it back over to Melody, I wanted to say a few words about a career in science, technology, engineering, and mathematics. An important thing to note is that you have to communicate your results and your work to your colleagues. We do that in many ways, through presentations like this, attendance at conferences, and writing technical publications and papers. You can see some of them here that our group has put out into the literature. It's extremely important to note that you need to have these skills as well to be successful in science, technology, and mathematics. Communicating is paramount to what we do so that your results are actually used and understood by the community and your colleagues. So with that, I'm going to turn it back over to Melody for some final comments.
Well, I hope that you have all enjoyed our presentation. We hope that you have learned something new and are feeling inspired, and all of our young budding scientists and engineers out there have something to think about as they continue on in school, because we have a lot of fun in our lab and we would love to have you all join us. So, speaking of inspiration, the movie that you all are going to be watching today is called Big Hero 6. And the reason that we chose this movie is because, for one, it focuses on scientists and engineers, which we really love, and they have a lot of fun with what they're doing. As well as the main character has a special technology that he uses. I don't want to give too much away, but he doesn't 3D print in the traditional sense, but he uses his technology to assemble these really interesting and complex shapes. So if you remember to what Will mentioned about architecture, while you're watching the movie, I want you to think about that, and I think that you'll know what I'm talking about when that scene comes up. So with that, I'm going to invite the rest of the team back here on stage, and we have a couple minutes for questions if anyone wants to pick our brains on anything. You have a question? The 3D printer colors? In these ones, or that were in the little vials that are on top here? And these ones? Yeah. So the question was, how are the different colors made for the 3D printer? And so these ones are all made out of these different type of thermoplastics. There's either PLA or ABS, but it's the similar material that's in Legos. And so we're actually able to purchase them with different colors. So I would assume it's probably a dye that they put into it. Okay. Do you have a question? Good question. So the question was, has there ever been a mistake with a 3D printer?
I would say there are more mistakes with 3D printers than successes. It's still a very early stage technology, and everyone likes to show all their successes, so it looks like it works every time, but in fact it doesn't. You have to go through many iterations and loops to get it to work right, to print the part that you want. But you learn as you go, and you improve as you go. So 3D printers fail all the time, but when they work, you get these tremendously interesting components and materials.
How about you right here? Say that again? So the question is, how much money are the 3D printers? This is interesting. So one particular company held the patent on 3D printers for a long time, and when that patent expired in 2007, 2008, it basically became an open technology. And so that's why you've seen such a large number of 3D printers out on the market. So you can get 3D printers for your home for as cheap as a couple $100 up to a couple $1,000. So there's kind of a wide range, but they're still becoming more and more accessible to people.
Just to add to that, those, what Melody is referring to are these plastic printers like the one you see up here. If you were to do it with metals, like Eric showed the selective laser melting with a laser, those machines cost on the order of $1 million a piece. They're very expensive. Not something you get for your home these days. Should we go to the back? How about this guy in the middle in the back? Yeah.
How long does it take to
How long does it take
make the 3D printer?
to make the 3D printer itself? Ooh, good question. Again, it depends on the printer. In many cases, we buy them. This one was purchased. And the company probably took days to weeks to build it. Something like the laser metal printers, usually if we order one of those, it takes many months before we get it. We also build our own printers, and those can take anywhere from a few weeks to months to years to get them to actually work right. Eric showed the holographic lithography and mentioned he's been working on that for a number of years. It's only just starting to work. So it really depends on the material and the technology. How about Ray?
I know you're talking prosthetic arms and hands. What are some other practical applications for the 3D printers?
So great question. The question was, they're making prosthetic arms and limbs and things like this with 3D printers. What are some other practical applications? So applications range from biomedical, implants like hip and knee implants and metals, limb prosthetics, things like that as you mentioned, all the way to consumer products like lampshades that are custom designed, to parts for the aerospace industry. I think again, Eric mentioned it, General Electric now is making the fuel nozzle in their latest jet engine entirely with metal 3D printing. And they're making 40,000 of them a year.
Well, you know what? Because we want to get to the movie, I want to kind of wrap things up and just, I have two reminders. One is that if you have a worksheet, please remember to get stamped between now and the movie. We have people manning the booth outside to get the stamps so that you can take your stamped worksheet back to your teacher so they know that you are here. And the second is that I want to announce the winners of our raffle, our random drawing, and you can go again out to the lobby to get your prize. Carlos McIger from Eisenhut School, Lena Infield from Fremont Elementary, and Mia Brown from Ustack Elementary. So congratulations. And I'd like to just take this moment to thank our presenters for a fabulous presentation.